from Beijing Institute of Technology in China. So he's going to talk about data-driven lithium battery model.
Okay, thank you for your introduction. Okay, hello everyone. Today I will talk about the battery management system in electric vehicles. Okay, firstly, before introducing the content of my research, I will introduce the background about the electric vehicle and the batteries firstly. Okay, the first is electric vehicle. With the growing concerns on the shortage of fossil fuels, the common sense has been reached that the electrification of automotive industry is the future trend in mitigating the energy issues. So the electric vehicles have been cited by lots of countries as both the short-term and long-term strategy to encourage the promotion of electric vehicles. And in China, electric vehicles is also one of the key area of Made in China 2025. And as shown in this figure, from 2014, the sales of electric vehicles have exploded. Okay, next, as the bottleneck technology of electric vehicles, the battery hosts the complex and hardly observable internal chemical reactions. And it is important to monitor and manage the batteries in electric vehicle during the whole life cycle and under multivariable environment. And in recent years, in order to realize the accurate state monitoring and management of the battery, the development of a flexible, self-configurable, and reliable battery model has become one of the most crucial technology for electric vehicles. Okay, next, this figure is the commonly used battery management system in electric vehicles, the main function of which is to measure, model, and management thousands of battery packs in electric vehicles, collecting and analyzing the battery operation data in real time, and providing an important fundamental for state of charge estimation of the battery. Okay, next, in recent years, there are a lot of researches on the state of charge estimation of the battery, as shown in these figures. And the most commonly used model is equivalent circuit model and the electrochemical model. And the commonly used algorithm is the least square algorithm and the Kalman filtering algorithm. And most of them are mainly focused on the state of charge estimation, parameter identification, and fault diagnosis of the battery and the battery management system. Okay, in our work, the concept of a cyber-physical system and the deep learning algorithm is used for battery modeling and management as well. And so before introduce the content of my research, I will explain why we use them. The first is a cyber-physical system. And as we know, as shown in the first figure, the battery management system in vehicle is the most commonly used instrument for management of batteries. But the data of which are generally derived from a single vehicle, the data volume and the calculating ability in which is limited. So it is difficult or impossible to manage the battery accurately under multivariable environment over the whole life cycle. So in recent years, the cloud-based battery management system is proposed in lots of research. But the cloud data center have advantages such as high storage stability and high calculating ability. But as we know, the system real-time performance is also conflict with system accuracy or stability, and this is more evident in battery management as well. So in our work to establish a battery model that has good real-time performance and stability, the concept of cyber-physical system is used in our work. And for deep learning algorithm, as we know, the chemical reaction in battery is complex due to the battery is a complex system due to its complex chemical reactions. So the deep learning algorithm is used in our work. And this figure is our proposed cyber-physical system-based battery management method. And it consists of three parts: the cyber physics, the cyber system, the communication network, and the physical world. And in cyber system, a cloud-based battery model is established, and a battery database is established too. And the battery data of all electric vehicles that share the same specification is uploaded to cloud in real time, and combined with artificial intelligence algorithm of deep learning algorithm, a battery model that is able to adapt to the change of environment and life state is established. And in physical world, battery management system in vehicle is used to manage the battery in vehicle in real time. And the difference is a data transmission model is set on the basis of BMS in vehicle, which enables the bidirectional link between the vehicle and the cloud. Okay, next, before we start battery modeling, the preparation work is indeed simple. And as the battery data is characterized by large volume, low value density, and error, so the first step is data cleaning. And as shown in this figure, the generalized regression neural network algorithm is used in our work to perform data cleaning tasks for its high speed and high precision. However, with the data volume increasing, the performance of generalized regression neural network is not satisfactory again. So it is difficult or impossible to build an accurate battery model under dynamic conditions or under the whole life cycle of the battery based on generalized regression neural network. So to overcome this difficulty, only a small part of battery data is used for trained model. Then that is the battery data near to the data cleaning point or position. And to obtain a high quality battery data cleaning model, the cross-validation technology is also used in our work to obtain the situable model hyperparameters in generalized regression neural network and the optimal training data sequence length. And if we try to establish an accurate battery model, it is necessary to quantify the degradation phenomenon during model of the battery, as the degradation phenomenon occurs with the use of the battery. And the rainflow cycle algorithm is used in our work to quantify the battery degradation phenomenon, and it is and the rainflow cycle algorithm has been commonly used in failure analysis field. And these two figures shows that battery charge and discharge profile after processing by rainflow cycle algorithm. The charge and discharge cycles is extracted, and the total number of cycles and the total depth of discharge are used to characterize the battery degradation phenomenon in our work. And in our work, the deep learning algorithm is used to establish the battery model. The current, the temperature, the state of charge, and the total number of cycles and the total depth of discharge is used as the input, and the terminal voltage is used as the output of the model. The battery modeling process is shown in this figure. The residue A and the residue B are used to determine whether the model has an overfitting problem. And in our work, the deep delight knife and the backing propagation algorithm is used to establish the battery model. And the deep delight network is used to extract the deep filters in battery data. And the backing propagation algorithm is used as the final output layer of the battery model. Okay, at last, to improve the system performance, we propose a conjunction state of charge estimation method between the cloud and the vehicle. And as we know, the Kalman filtering algorithm is one of the most commonly used algorithms in the field of battery state of charge estimation. So it is also used in our work to perform the real-time state of charge estimation in vehicle. And the difference is we use the state of charge estimation result in cloud as an additional observation variable in algorithm. And for the parameter identification and the state of charge estimation process, so also the accuracy and the real-time performance of the system can be achieved at the same time by the conjunction working between the vehicle and the cloud. So this is our result and the result part. And to verify our proposed model, the data of electric buses are collected during normal driving, and we use it to train our model and verify our model. And these two figures shows the data cleaning model proposed in this paper. And the sampling frequency is set as 1 second, and the data loss value is set as 1/5. The missing variable is assumed as the terminal voltage and the state of charge. And by the proposed generalized regression neural network, the maximum relative error can be limited with 5%. And these four figures shows the accuracy of cloud-based battery model in different state of charge levels. The left one is the model based on neural network algorithm. The right one is the result of deep learning algorithm-based model. And when the state of charge is between 70% to 99% and 5% to 40%, the accuracy of deep learning-based model is much greater than that of neural net algorithm-based model. The reason is that the deep learning algorithm can fully utilize the deep filters in data. And the accuracy of different algorithms is also compared in our work. And this table shows that the deep learning algorithm-based model is the accuracy of deep learning-based model is much higher than that of Bayesian propagation network, extreme linear motion, and split vector regression. And at last, to verify our proposed battery degradation quantifier method and the modeling method, we select a battery that had been used for 6 months as experiment object. And the result shows that when the model input is only the state of charge, the current, and the temperature, the estimated terminal voltage is generally higher than accurate value. The reason is that the electromotive force decreases with the battery degradation phenomenon, but this kind of decreasing is not able to consider it in battery model. And after the total number of cycles and the total depth of discharge is introduced as additional input, the model accuracy is improved significantly, and the mean absolute percent error is within 2.5%. And finally, these two figures shows the state of charge estimation result. And the first figure is based on deep learning algorithm, and the second figure is based on the conjunction state of charge estimation mode between the vehicle and the cloud. And from the figure, we can see that the the state of charge estimator can work stably under these conditions, and the maximum relative error can be limited within 3%, and the mean absolute error can be limited within 1%. Okay, that's all. Thank you for your listening.
When you do this test, is it real-time test of the model? So you compare your modeling result with the original battery data?
Real-time performance?
Is it a real-time estimate of the...
Yeah, this figure is the real-time, and this is a charge and discharge experiment on a single battery pack, and it is not for the whole battery pack. And the experiment is the battery is placed in a 25-degree chamber and loaded with urban dynamometer driving schedulable conditions. And this is a real-time performance test. This is a result in battery management system in vehicle, and this is included. This is not the real-time model, and this is a real-time model. And this model can be used for battery management or vehicle energy management.